Okay, let's talk about ionic equations. We are going to do a specific equation today. We're going to talk about potassium sulfide and aluminum acetate. Now notice that I have these written out in words, not in formulas, and that is something you'll have to notice because we're going to do that for the rest of the semester for the most part. You'll see mostly the words written out, and you will have to take that name and turn it into formulas. So don't forget to be reviewing those formula writing rules that you learned earlier in the semester. All right, we're going to do four things with this combination of chemicals. We're going to predict what our products will be. We're going to write the balanced molecular equation, write the total ionic equation, and then the net ionic equation. So first of all, predict the products. Let's write our two compounds down. We have potassium sulfide and we have aluminum acetate. Now, this is going to be a typical double replacement reaction. Historically, that's what we would have called it, double replacement reaction. You probably heard that term in your 101 class or your high school chemistry. It's also sometimes called double displacement or even metathesis. That's kind of an old-fashioned word for it. What it basically means is that these two compounds are going to swap partners. In our book, we are going to even further categorize it, not just as a double replacement reaction, but as a precipitation reaction. In order for a double replacement reaction to occur, there has to be some reason for it to occur. And in this case, it's the formation of a precipitate. So let's look at what partners we have. Our cation here and our anion, because these are both ionic compounds, when we have the cation here and the anion here. Now, in swapping partners to get the products, we need to be careful to take the cation from one compound. Oh my goodness, we have an alarm going off here. Let me shut that off. And the anion from the other compound. Put them together, and we'll have potassium together with acetate. Notice I don't bring the subscripts along. I don't have to have two potassiums for every acetate like I do for the sulfide. I don't need three acetates for my potassium like I do for the aluminum. So we're going to look at this compound just on its own merits and decide what kind of subscripts that those ions would need. And in this case, potassium's a +1, acetate's a -1, so that's good. Now, let's grab the other two. We have the sulfide going together with the aluminum. The aluminum is the cation, so it gets written first. Aluminum and then sulfide. In this case, aluminum is a +3 ion and sulfide is a -2, so we're going to have Al2S3. Let's go back to the description of the problem. Consider the combination of aqueous potassium sulfide. Oh, so our original guy was aqueous. That means dissolved in water. And so was the aluminum acetate, dissolved in water. And let's look at our two products. If you grab that chart that I uploaded in the content section that is solubilities of ionic compounds, it's basically a reworking of the table that's in your book. I thought was harder to read. I like my version better, but both of them have the same information. If we look up, the first rule says group 1A and ammonium compounds are soluble. Anything that has a group 1A ion in it. Well, potassium is a group 1A ion. So that means any compound containing potassium is always soluble. So we'll put an AQ after the potassium acetate. If you go down a couple lines, you'll find out that all acetates are also soluble. So this guy had no chance. He has to be soluble. All of the rules on that table are for anions, except for the very first one with the group 1As. So for our aluminum sulfide, we will look down the chart at sulfides, which is almost to the bottom. Don't confuse it with sulfates. And it says that most compounds are insoluble. There's only a few soluble exceptions, and aluminum is not listed there. If it's insoluble, it means it does not dissolve in water, so we put an S afterwards as the state to say solid. That S is not for soluble. which is confusing. AQ is for soluble because it's aqueous, it dissolves in water. S is for solid. That means that this is going to be our precipitate. And the formation of that precipitate is what makes this reaction happen. And sometimes precipitate can be abbreviated as PPT. All right, so now that we've figured out what our compounds are, let's quickly balance this reaction. K2S plus aluminum acetate is going to produce aluminum, and it doesn't really matter which order you write these two products in, aluminum sulfide solid plus potassium acetate aqueous. If we balance this, we're going to need a couple of aluminums, we need 3 sulfides, and that gives us 6 of these guys. So there we are, balanced. Now let's put in our AQs here that I left out on the left side, okay, so that we know what we're dealing with. The total ionic equation is supposed to show us not just the formulas that we have in the balanced equation, but what happens when these guys go into solution. In solution, when these dissolve, ionic compounds break up into ions, and so we're going to have, for each formula of potassium sulfide, we're going to have 2 different potassium ions and 1 sulfide ion. That's what we're going to get when it dissolves. The water molecules come and surround each one of these ions and hustle them away into their own little groupy cluster, and they don't associate with each other anymore. So be careful not to write K2. The 2 Ks, the 2 potassiums, are not associated with each other. And since they're not, we have to write 2K plus to show that they're 2 independent K pluses. It's not a K2 plus with a little subscript, because that would say that those 2 potassium ions were bonded together, and they are absolutely not. They're repelled by each other because they are both positive. Then our sulfide ion goes off separately as well. So this is what we write in the ionic equation to show this is really what we have in solution. We don't really have K2S's floating around. We have individual K pluses and individual S2 minuses floating around in solution. Now the same thing is true of the aluminum acetate. The aluminums don't go off with the acetates. They separate into individual pieces because they're ions. The water molecules are attracted to the ions and take them around individually. And so each aluminum acetate breaks up into 1 aluminum ion and 3 acetate ions. Now, looking back at my original equation, I notice that there's a coefficient in front of these guys. So really, I don't have 2 potassium ions. I have actually 3 of those formulas, and each one turns into this combination of 2 potassium ions and a sulfide ion. So really what I should have written there is a 6 potassium ion and a 2 for my sulfide ion, because there were 3 formulas. Each formula broke up into 2 potassiums and 1 sulfide. That gives me 6 potassiums and 2 sulfides. The same on the next one. I actually have 2 formulas worth, so I have a 2 aluminum ions, and again, since each formula had 3 acetate ions and there were 2 formulas, that gives me 6 acetate ions. Moving over to the other side of the equation. Aluminum sulfide is the precipitate here. It is a solid. It is not actually going to dissolve in water. Since it doesn't dissolve in water, it's insoluble. It doesn't break up into ions. The ions are more attracted to each other than they are to the water, and so they stay together in a lump, in a great big crystal with billions and trillions of ions in rows, bonded to each other. It doesn't have anything to do with the water, and so we do not break it up, because what we're trying to do in this ionic equation is to show actually what we have. What we actually have is aluminum sulfide crystals where they are not broken up. And going to the last thing in our equation, we have potassium acetate and we have 6 formulas of those, so we're going to get 6 of each of those ions, all separate from each other. So we don't want to put a subscript of 6. We want to show that by putting it as a coefficient that they are individualized. Now, if we look at this total ionic equation that we have made, we notice that some things on the left and the right are exactly the same. There's 6 potassium ions on the left, and there are 6 potassium ions on the right. You can see that those are identical to each other. They have the same charge. That's really important. They have the same charge. It's very important to put your charges in on these ionic equations, so be sure you do that. But these 2 potassium ions have exactly the same charge. They don't do anything. They are not reacting. They are just sitting there watching other people do all the action. Since they are not reacting, they are not involved in the action, we call them spectators, or spectator ions. If you go to a football game and you just sit in the stands and watch, you're not really causing anything to happen. You're not scoring any touchdowns, you're not doing anything very exciting, and all you're doing is watching the other folks do the action. And the same thing is true for the acetates. They are just spectator ions. They're not doing anything because they're the same on both sides. Normally we don't draw these arrows that I'm putting in here, I'm just trying to illustrate what's going on. So I'm going to say now the 6 potassium ions are the same on both sides, so I'm going to draw a big slash through both of them, and I recommend you do that. Draw a slash through the 2 acetates to show they're exactly the same on both sides. If you subtract the same thing from both sides of an equation, you know this from math, you haven't changed the value of the equation at all. So we're going to subtract the potassiums out of there, we're going to subtract the acetates out of there, and we're only going to leave the species that are actually involved in the action. So what we really have left over after we take out the spectators is the net ionic equation. And you know that somehow, look at this, I put a 2 there. Oh my gosh, it should have been a 3. All along, that should have been a 3. You're probably sitting there wondering, why did she put a 2 there? Okay, that was a 3. You didn't see that 2. It's just a 3. Plus 2 aluminum ions are left over as well. And those two types of things come together. Those 2 different ions come together, tons of them, to form the aluminum sulfide. So when we are actually doing our reaction, we're dumping a solution that has a bunch of potassium ions and sulfide ions. That was our original guy here. And we're dumping that together with a solution that has a bunch of aluminum ions and acetate ions. We're putting those 2 solutions together, and the aluminum ions and the sulfide ions find each other, are very attracted to each other, much more so than to the water, and they immediately start crystallizing together and forming large crystals that then fall to the bottom of the container as a precipitate. And that is our net ionic equation. You know that net means what's left over after you take things out, right? I mean, your net pay is what you have left after they take a bunch of stuff out for taxes or whatnot. Your net worth is what you have after you take away what debts you have. So net means what you have left afterwards. So after we take out the spectator ions, what we have left afterwards is our net ionic equation. This is showing in a much more realistic fashion, in a much more true fashion, exactly what is going on in this reaction. The balanced molecular equation is useful because we can't just go to a shelf and pull off sulfide ions. And so it shows what we are actually combining to make this happen. But on the level of the atoms and the molecules, what's really happening is these ions on the left are getting together and forming crystals that show what we have on the right.